So in this video, I'm going to talk to you about what it means when we write these reactions. What is the interpretation of the reaction? So we've spent some time figuring out how to balance them so that there are the same number of atoms of nitrogen on this side and nitrogen on this side, and then there's 6 hydrogen here and 6 hydrogen here. But we don't stop to talk about two what? We read this as 2 ammonia and 1 nitrogen and 3 hydrogen, but we don't put a unit in there typically. So what does it even mean, and how do we use it? The word that's supposed to go in here is, in this case, molecules, right? We talk about particles. There's 2 particles of ammonia. Well, ammonia, as being made of all nonmetals, is a covalent compound, and covalent compounds come in molecules. Okay, even my nitrogen and hydrogen over here, because they're diatomic, these are also molecules. So I have 2 molecules of ammonia will react to form 1 molecule of nitrogen and 3 molecules of hydrogen, but the reality is that you would never ever take 2 molecules of anything and expect to watch 1 molecule form and 3 molecules form. It's just silly. Another thing I want to point out before we get any further is molecules don't get conserved. Remember, atoms did. I have 2 nitrogen atoms here and 6 hydrogen here, and I have the same number on this side. My atoms get conserved, but down here, my molecules don't, because we're talking about groups of things. Okay, I can have 2 big groups, or I can end up with 4 little groups and still have the same objects present. Okay, the other thing we're going to look at, again, you're never going to have 2 to 1 to 3. It's a ratio. This is the lowest terms ratio of these molecules, which means I can actually have however many I want. I can multiply this by anything, and as long as I multiply everything by the same thing, I still end up with the same ratio. So I could multiply everything by 2, right? And then I would end up with 4 molecules of ammonia and 2 molecules of nitrogen and 6 molecules of hydrogen. And I still have that same ratio, but it's still a little unrealistic, right? Really small. So let's think a little bigger. Well, we're going to try dozen. We're going to multiply by 12. But instead of writing it as 24 and 12 and 36, we are going to just call them dozens. So I'm going to say I've got 2 dozen ammonia. And now I'm going to take the molecule out and assume that dozen means 12 pieces of something. So I have 2 dozen ammonia, and I have 1 dozen nitrogen and 3 dozen hydrogen, and I have the same ratio because I still have the same substances, right? I multiplied them all by the same thing. I multiplied them all by 12, right, to get the same basic idea. Once again, 12, kind of small. I could do the same thing like with a million, though. I could say 2 million here and 1 million and 3 million, and that would work, but even that is really too little when we're talking about particles as small as atoms. So the number we're going to multiply by is 6.02 times 10 to the 23rd. 6.02 times 10 to the 23rd. That number is a mole of something. The term we use is mole, and it's usually spelled M-O-L-E. Okay, I'll write that over here. 1 mole. Okay, but we drop the E to shorthand it like we would grams, becomes a G. I know it seems silly, but you'll get used to it. And now I've got 2 moles of ammonia, 1 mole of nitrogen, and 3 moles of hydrogen. What this is going to do now is make these big enough to actually see and to work with. So if I'm going to really use these chemicals and measure these chemicals, I need them in a quantity that I could actually dish out onto a balance or measure a volume for, or something that I can see even. Okay, and mole is about how big that needs to be. Now, why exactly this number? There's a reason, and we'll talk about it later, but trust me that for right now, it doesn't make a difference. 6.02 times 10 to the 23rd anythings equals 1 mole, just like 12 of anythings equaled 1 dozen. Okay, so what do we do with that? Well, the first thing we're going to do with it is create what are called molar ratios, which are exactly what they sound like. Okay, I have some definition. It's not great, but it's a definition. It is, for our purposes, a molar ratio are going to be fractions that show the ratios in which 2 substances react. Okay. or they're produced, or one reacts and one's produced. It doesn't matter. Okay, all you have to do, we need a balanced chemical reaction like we have here, okay, and the coefficients on that balanced chemical reaction are going to become numbers of moles, and then we're going to make fractions out of any two substances in that reaction. So I can take this reaction, right, assume that that means 2 moles and 1 mole and 3 moles, and I can start making fractions out of that. So I'm going to scoot it up so we can see them right here. Okay, I can say 2 moles NH3 over, we'll say 1 mole of N2. That's a molar ratio. I can flip it over. We're going to see here in a few minutes. There's a reason we might want to do that. So I could say 1 mole of N2 to 2 moles NH3, right? I can also pull any other two substances I want out of this. So I could say that I have 1 mole of N2 over 3 moles of H2. Okay. Or I can flip that over, or I can talk about moles of ammonia to moles of hydrogen, and it does not matter. As long as I'm pulling two substances from this reaction, okay, that I have balanced, and I'm using these coefficients right here as my number of moles, that's going to give me a useful molar ratio. Okay, so once again, what are we going to do with that? Well, I'm going to give you a little bit of background information. We're going to come back to these molar ratios here in just a second. Okay. The process we're going to use, it's called dimensional analysis. Okay. What that means is we're going to make conversions using relationships between units. And another word for units is a dimension, right? When you talk about like what are the dimensions of that, it's 5 meters by 2 meters, right? That's a dimension. So we're going to make changes in units using our relationships, using equalities, things that we know are true. Okay, for example, okay, if 1 foot is equal to 12 inches, okay, then I know that I can write a ratio for this of 1 foot over 12 inches, and that's going to equal 1, right? Because if these two things are equal to one another, and I make a fraction out of two things that are equal, then I'm going to get 1. Just like if I took 2 times 5 and I divided by 10, those two things look different, but this is 10 and this is 10, and it's still going to equal 1. Okay? So if I want to know how many feet are in 193 inches, the way we're going to do this, okay, is we're going to write down 193 inches, and then we're going to draw a line under it. We're going to make that go out nice and far. Okay, this line right here is a fraction bar. Right, it's a big division bar. Okay, we take the numbers on top and we divide them by the numbers on the bottom, just like we've always done. Okay, then I'm going to draw a line right here. Okay, I'm going to call this a multiplication bar. I know that's not a thing. Okay, really what that is, it's a parenthesis. Okay, it closes off this 193 so that it sets it aside, and I can tell the difference between this and the next thing we're going to write in here. Then I'm going to take what I call a conversion factor. That's this fraction up here that's made out of 2 equal parts that equal 1. Okay, so that's here. This whole thing is our conversion factor. Okay. Now I know that 12 inches is equal to 1 foot, or we'll do it the other way first. Okay. Now I know that 1 foot equals 12 inches, right? I can set it there, but I can also flip that over and say that 12 inches equals 1 foot. And the direction that I want to put this is up to me. But because they're both equal, it doesn't matter what direction I divide them, they're still going to equal 1. Which means I can multiply by this thing all I want and not change how big this number really is. It might look different, but because they are equal to 1, then it doesn't matter that I multiply by it. It's not going to change my original value. Okay, so how do I decide which way I want it to go? Well, I have inches, right? And I want to cancel them out. my units are going to behave like variables. So if I have inches on the top here and I divide by inches down here on the bottom, then I would be able to cancel them out. So I'm going to take my conversion factor, okay, and I'm going to tape it down right there. Maybe. Okay. Like that. Okay. And I can see that I have inches on the top and I have inches on the bottom, and I can just cancel those two things out. So if I take 193 divided by 12, okay, that will give me my final answer up here. And honest, I forgot to grab a calculator, so give me like 2 seconds. We're gonna get our calculator out and we're gonna take 193, okay, divided by 12, and it's going to tell us 16.08, and it goes out with some decimals, but we don't care. Okay, don't forget to put a unit on it, right? Now we're measuring things in feet. Okay, I had inches, I canceled my inches, and I'm left with feet. Okay, so yes, no, you won't actually see these problems, but I'd like to show them to you in terms of feet and inches, just because we understand this equality. Okay, so another equality we know, like I was talking about earlier, is that 1 mole of anything, so we'll say ammonia, is equal to 6.02 times 10 to the 23rd molecules of ammonia. So if I want to know how many molecules of ammonia are in 1.2 moles, I do basically the same thing. I write out the number that I'm given and I draw a nice long division bar, okay, and I put a little multiplication bar, parenthesis, right next to it. Okay. And then I look at my options. These two things are equal, so we're going to make a fraction out of it. I have 6.02 times 10 to the 23rd molecules over 1 mole, or 1 mole over 6.02 times 10 to the 23rd molecules. Again, we have moles on the top, and we want to cancel them out. So whatever's here is going to drop down to the bottom. Okay, so I want moles to end up down here, and we're going to put our conversion factor just like that. Okay, so 1.2 moles NH3, then we're gonna, again, put the moles on the bottom, so those two things will cancel, one on the top, one on the bottom. Careful not to cancel your numbers, we're just canceling the unit, okay? So to find our answer here, we're gonna take 1.2 times the 6.02, right? We're gonna multiply everything on the top of the fraction bar, and then we're gonna divide by everything on the bottom. Now, buttons on your calculator, 1.2 times, on my calculator right here, I'm going to go 6.02, and I'm going to push this button that says EE 23. Notice I never push times 10 to anything. Okay, and that's going to give me an answer. Okay, and that is 7.224 times 10 to the 23rd, and we need a unit, molecules, NH3. Every answer needs to have a unit and what we're talking about. Okay, I have 2 more problems that we're going to work through. Okay, with some different situations. Okay, next question: how many moles of nitrogen will be produced if 2.8 moles of ammonia react? Well, now I'm talking about 2 different substances, correct? Which means I'm going to come back here and use these molar ratios that I wrote a little while ago. Okay, and these are going to be my new fractions, but I'm going to set this up exactly the same, and we're going to say 2.8 moles NH3, and we're going to draw ourselves our division bar and then our little parenthesis to block it off, and we know that I've got moles of NH3 here, which means I need them down here, and I'm trying to go to moles of nitrogen. Okay, so we're going to take this one right here that's got moles of NH3 on the bottom and a mole of nitrogen here. 2 mole NH3 will equal 1 mole of N2 in that balanced reaction, right? All right, so our answer here, 2.8 divided by 2 times 1, we're going to get 1.4 moles N2. Okay, last one. What would happen if I needed to know the number of hydrogen molecules produced when I have 41.8 moles of nitrogen produced? Okay, we start with whatever you're given. It does not matter what's produced or what's reacted. The number you're given is the number you're going to start with. Okay. Just because you start with a chemical doesn't mean that, like, just because I start with ammonia in this reaction doesn't mean that ammonia has to be the first thing in my dimensional analysis. I start with the number that I'm given. This is the information I have to work with. That's where we begin. Okay, we need to get to hydrogen molecules, but you'll notice that right now we're still talking about nitrogen. In order to get to hydrogen molecules, you have to have moles of hydrogen. So here, let's look at where we are and where we're going. We have moles of nitrogen. The first thing I'm going to have to do is to change this to moles of hydrogen, and then I can find molecules of hydrogen. Okay, so I have moles of nitrogen here, which means, again, whatever's here has got to go down here. Moles nitrogen, and I want to go to moles of hydrogen there. Okay, we're looking at a ratio of moles. That comes from our balanced chemical reaction. Okay, I have 1 mole of nitrogen for every 3 moles of hydrogen. So I can come in and put the numbers in, 1, 3. Okay, and then we're going to draw another one, okay, and just keep going across with the same problem. Okay, now I have moles of hydrogen here. We're going to drop that down to the bottom. Moles, H2, drop to the bottom here, and I want to go to molecules of hydrogen. Okay, well, the equality between moles and molecules is that 1 mole is equal to 6.02 times 10 to the 23rd. Okay, and that will get me to molecules. You'll notice that moles of nitrogen go away, moles of hydrogen go away, and we're left just with the molecules. Okay, so we get a calculator. There. And we say 41.8 divided by 1 times 3, okay, divided by 1 times, again, 6.02 times 10 to the 23rd equals, okay, and my answer will be 7.5, we'll round 5 times 10 to the 25th molecules H2. Okay, good luck.